I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Hey, Jam, guess what?
What?
We have a new patron to shout out today.
That's right. When we get new patrons, we shout you guys out at the very beginning of the next episode. And we haven't recorded in a while, but we are very excited to welcome Venus to our super cool community of patrons. Venus, thanks so much for joining, supporting the podcast.
Yeah, welcome to the party.
Excited to have you.
Yeah, so this episode is dedicated to you, Venus. Here we go.
Yeah.
So this episode is also dedicated to other people too.
Yeah.
Those who asked the question.
Yeah.
So maybe I'm going to get some flack for the title that I want this episode to have. I guess we haven't named it yet, but I want it to be named Why Freezing Points Aren't Real, and also Why We Salt the Roads in the Winter.
Okay. Nice.
Because we've alluded to and talked about briefly freezing points before, but I don't think we've ever done a whole episode about it.
I feel like it may have happened in a Q&R.
I think so.
Like there's a lot of times when we have like a vague memory of like, we have addressed this. Because like, especially for me, because I'm not otherwise, other than the podcast, not hanging out in the world of chemistry super often. So if we have like a vague idea of talking about it, it's like, it probably did happen either on our way to another episode explanation or like during a Q&R where we briefly touched on it.
And it
like
could
that.
have also come up when we talked about why your pot didn't boil that one time.
Yes. Right. Yeah. Which that's been a long time ago. So
A long time ago.
no surprise there that we wouldn't fully remember.
So this might be some older information, not as much new information for you, but I get asked these types of questions every winter. And so I thought it was time. It's time.
Yeah. Yep. And we just had a recent example, and anyone who lives kind of in the states near us has had a recent reason to wonder these things.
Yes, there was a great freeze.
Yeah.
In fact, we were supposed to record this episode a week ago and we got iced out.
That's right. So it's been a little longer than normal since we've recorded.
Yeah.
But, and that's why. But it also helped because now this topic
came
is related.
up.
So
yeah, we were going to do the old COVID remote recording, but we got thunder sleet.
Yeah.
Thunder sleet, a new meteorological phenomenon that I never knew about before in my 30 years.
They just keep coming out with meteorological phenomenons every once in a while without any warning.
I know. I
so
was
frustrating.
Like, I don't know if you're allowed to have the thunder sleet storm. Okay, so anyway, with that, our local listener, Tim, who's also a chemist and a member of our Patreon, he told me that someone asked him why we drip water in pipes to keep them from freezing.
Oh, right. And the person, he said they live somewhere like more temperate.
Yeah.
And so they don't ever have to do that.
Never have to do that. And for people who live in probably better infrastructure places with pipes that are built to withstand regular freezing, they might not have to deal with this either. But in Texas, our pipes aren't made for that. So we're instructed to keep them dripping to keep from freezing.
Right.
So that question came up. And then also, I usually get questions around this time of year about why we salt the roads. So one of our listeners, Jonathan, asked about that as well.
Oh yeah, and we did get into that in the past. That's one of the ways we've touched on this topic is the salt roads thing. Plus, we talked about other ways, sugaring roads.
Yes, that's a very oldie. Our Steven sent that question in.
Yeah, that's right.
So we have touched on this before, but you know, I really just wanted an excuse to complain about freezing point. So that's what this whole episode is going to be.
Sweet.
And we'll answer those questions as well.
Yeah.
Okay, so have you ever done that thing where you have liquid water in the freezer and then you take it out and you hit it and it immediately turns to ice?
I have, and I've done it, but I never understood it. Or I didn't until this podcast. But I remember doing that like in like middle school.
Yes.
And like putting it at the back of the fridge where it's like super cold, but not quite cold or whatever. And it doesn't freeze, but until you do that.
Yes. So that's a thing called supercooled water that it's cooled below its quote unquote freezing point.
Right.
And that is a really good segue into why I think that freezing points aren't real.
Okay.
But we're going to talk about what all the states of matter are first so that you can kind of come alongside me while I paint the picture.
Okay.
And we've talked about these before, but I think it's always really good to review. And also I think it's really good for maybe for people who aren't chemists or who don't maybe think like a chemist, though this is how I think about states of matter.
Right.
So come along into my brain.
So it sounds like you're saying basically we all kind of know some stuff about states of matter.
Yes.
But it's important to state the states of matter because they matter.
I thought you were really going somewhere with that. But also what you said wasn't wrong. So yes.
It wasn't a total off the
begrudgingly yes. Okay, so I think of matter and the states of matter at a molecular level.
Okay.
So that would be the solids, the liquids, and the gases. And there's some gray area between those, but solids are typically crystalline, which means they have an order to them. So if you imagine, say, several water molecules will form into a hexagon, and then several more water molecules will do that. And it's almost like you can stack the hexagons on top of each other.
Right.
So it's very ordered. There's like a very repeating structure.
Yeah.
Another way that it's sometimes depicted is if you had, say, a cube, and there's several cubes repeating over and over everywhere you can think, up and down and side to side. That's another way you can kind of think of the molecules. They're arranged in the lowest energy way that's like the best for them to be.
Okay.
And
that's specifically solids.
That's specifically crystalline solids.
Okay.
There's also amorphous solids, which we talked about in glass, which they have the other properties of solids that the molecules are held tightly together by the attractive forces that hold molecules together. Those are intermolecular forces. But they don't have the nice repeating structure.
Right.
So glass is one of those. It doesn't have the nice repeating structure.
Okay.
And I also mentioned one other one that sometimes will crystallize right in front of our very eyes. Do you remember?
One other one that sometimes will crystallize right in front of our
I'm saving some of this right now so that I can make a TikTok video about it and an Instagram reel. It's okay if you don't remember. It blew my mind.
Oh, wait. Is it honey?
No.
Okay.
That was a good guess. It's medicine like ibuprofen.
Oh,
remember
yes.
vaguely?
Yep.
And sometimes you'll pull it out of the cabinet after it's been there too long and it'll be sparkly.
Yep.
Because it's literally crystallizing. It's been solidified in an amorphous state, so it's easier for our bodies to break it down. And then it crystallizes over time.
So you're not a doctor, not a medical doctor.
Not a medical doctor.
Can I still take the crystallized medicine?
You can, but I think it would be less effective in my non-medical doctor opinion.
Okay.
You should probably ask your close personal relationship that is a basically medical.
Well, I was asking to help me in the argument that we have going on, which is that my medical professional spouse thinks you shouldn't.
You probably why bother? Ibuprofen's pretty cheap.
Yeah, but also when you need it, you need it. It's like I have a headache. I'm not going to the store right now. I'd rather take slightly less effective ibuprofen that's right here in the cupboard.
Listen, she might know something I don't know, but I would probably be like, it's fine.
I think I'm content with the answer that's less effective, and I think she'd probably agree with that. But I think I'm okay with less effective, but on hand.
What's her argument?
I think she thinks that if it's visually different, you shouldn't risk it. Basically,
yeah. And there could be something like it messes up a ratio.
Yeah, and plus, like classic medical professional, like caring about the details because they matter, and sometimes you could die if you don't.
The details do matter, and I wouldn't say that for every single drug. I would only say that for ibuprofen, probably because I'm relatively confident that it's safe. But I'm not a medical doctor, and that's just what I would do.
Yeah.
And we all know I have questionable practices in some ways. So.
And I definitely do. And I'm not a doctor of anything. So chemistry, medicine, anything. So.
Okay. So, there's amorphous solids they have those properties of a solid. They may flow over time at a very, very, very slow rate, but they're might as well be solids. They're considered solids.
Okay.
Now I guess I want to say these molecules are held tightly together by the attractive forces between two molecules.
Okay.
We've talked extensively about those intermolecular forces. We're not going to talk about them today. I'm just going to call them, attractive forces between the molecules. These are what hold two molecules together. And also when I talk about this, I think of a pure substance. So all water molecules being held together.
Right.
Or all sugar molecules in that crystalline state. We're talking about all of one thing.
Okay.
And turning to a liquid is different than dissolving. So we're not talking about dissolving. We're talking about one pure substance going through the phases from solid to liquid to gas.
It's kind of easier to observe and like differentiate those characteristics if we're just talking about one thing.
Yes.
And it gets weirder if you...
Yeah.
Okay, got it.
Yeah, and we can talk about what happens when you mix other things in, and we will at the end.
Okay.
But right now, we're just talking about you have a bunch of water molecules, just a whole pile of water molecules, and that's, not 100% accurate of what comes out of your tap because there are some salt and things in there, but it's easier to visualize it that way.
Right. Okay.
Now, to take a solid, which is held together by these attractive forces, and turn it into a liquid, you have to put in energy.
Right. Okay.
So usually energy is heat or light.
Okay.
That's what I think of when I think of energy for the most part. And energy translates to, molecules being able to move. And even in the solid form, the individual molecules can kind of like wiggle around,
Mm-hmm.
They have a little bit of freedom to move, but they're not able to change their position too much relative to the other things.
Right.
They're not flowing,
Right.
They're pretty stuck where they're at.
Right. Okay.
Just as far as I know. There might be some crystalline solid state chemists who come out here for me and they're like, here's all the ways it moves. But for what we have, this is a good understanding.
Yeah. Or at least it moves significantly less than its liquid counterpart.
Right.
So, yeah.
So now when we get to the liquid state, things are able to flow around. We've put enough energy in that there's still those same exact attractive forces, but we've put enough energy into the molecules that they have the energy to overcome the attractive forces and move around.
Okay.
So I try to think of an analogy for this. And the best analogy I could come up with is imagine you have a family with triplets. So they're all the same age and they have the same things attracting them to stay home and live with their parents.
Okay.
So those are the attractive forces, the things keeping them part of the family unit in their parents' house.
Got it. Okay.
Now, if one kid doesn't have a job at all, they'll mostly have to stay home, stick with their parents, eat with their parents, give them to eat. They won't be able to do very much.
Okay.
They may be able to move around a little bit, like maybe they'll get some birthday money or something. But for the most part, they're stuck with the parents.
Got it.
So in that scenario, the things that make it nice to live at home, a bed, a roof, food, those are the attractive forces. And money is energy. So that person doesn't have a lot of money to go out and be independent.
Got it.
Now, the liquid state, maybe they have a part-time job. They can't afford to live by themselves. They can't overcome the attractive forces of the food and the home that their parents provide.
Right.
But they do have enough freedom to maybe buy a car, maybe go out with their friends, maybe eat something different every once in a while. But they're still part of the group. They still live at home.
Right.
So that's what a liquid state would be. It has enough energy to kind of move around. The attractive forces are the same as they always were, but because there's more energy, they're able to move around.
Okay.
And then if you can put more energy into the liquids, you'll turn them into gases.
Right.
And gases are essentially independent molecules doing their own thing. They are moving around in a lot of empty space. There's if you imagine the concentration of a liquid and then spread it way, way, way out, gases can kind of go anywhere. It's an individual molecule moving around. And sometimes they'll have temporary interactions with other molecules that they come into contact with, but for the most part, they are fully independent molecules.
Okay.
Not part of a body of water, really.
Okay. So that's what I was going to ask is I've never thought about this until that moment, but in our air right now, we know there's some water molecules hanging out.
Right.
Would it be most common for it to be literally just one, H2O, doing its own thing? Or might it be two or three, what, or do we even know what's more common?
I don't know what's more common. I think
state
of it as mostly individual molecules moving around, and they will maybe temporarily come together in groups, but then keep spreading around.
Right. Okay.
And if it's colder air, they'll come closer together. Remember, colder air is more dense.
Right.
It'll bring it all in. But warmer air, they have more energy, so they can spread out even more.
Right. Okay.
So even if you have a lot of money, you can travel all over the world. But if you just have enough money to get your own house and buy your own food.
Yeah.
You're independent, but you're not as independent. So
Right.
there's still levels to it.
Yeah.
So a gas is like the third kid who same attractive forces keeping them at home, but they have enough money or energy to go get their own space.
Go travel the world, go
Mm-hmm.
backpack across Europe or something like that.
They've broken free of the group. They're independent.
Okay. Got it.
So that's how I imagine the states of matter. It's like literally in my mind, I could have like a picture of a bunch of really nicely ordered, maybe like marbles. Maybe you could imagine it like marbles in like a solid cube being held together, in a nice like box. And then the liquid state, they're in a bag maybe. So they're moving around more, but they're not just going everywhere. And then the gas state, they're just like marbles wherever they want to go.
Okay.
That doesn't capture the attractive forces very well, but it does capture like what the molecules kind of look like in my mind.
Yeah.
So that's the states of matter.
Okay.
And that is how I imagine them. And in this description, when I talk about increasing the energy, we are assuming a constant pressure because you and I have talked about before, pressure can impact things. So if y'all want to go all the way back to the episode about how Jam's pot of water never boiled, water boils at a different temperature on like the ocean floor than it does at the top of a mountain.
Right.
Because of the pressure. So we're talking about, we're just keeping the pressure constant. We're not thinking about these other factors. We're just talking about all things held constant except for the energy we're putting in. The temperature heats up and it goes from a solid to a liquid to a gas. So, but the problem that I have, I guess, with freezing is that it's kind of the reverse process.
Right.
Instead of thinking about putting energy in, we're thinking about taking energy out.
Mm-hmm.
And I feel like that's one of those gray areas that we don't really talk about, which is I think of, and I think most scientists think of this like this, we're putting energy in and the molecules are moving around more and more and more. But then sometimes we're taking it out. So sometimes it goes the opposite way where we're removing energy. And just like I talked about with the cold air, then the air gets a little bit more dense.
Yeah.
And eventually it will condensate like on the outside of a cup.
Mm-hmm.
If you've ever seen those water droplets build up, that's condensation because there's right in that area around the outside of the cup, there is not enough energy for those water molecules to stay free.
Right.
They've lost their job or whatever. And I feel like it kind of is like after you've maybe moved out of your house and gone to college and then you come back in the summer, you're not really moving home.
Yep.
But so it's like so I feel like the reverse process is a little more complicated. Or maybe you're between jobs, so you're home for a little bit, but that doesn't mean you're like moving back in.
Yeah.
This is how I feel about freezing. It's the reverse process. It's a little bit more complicated.
Got it.
So I think the part that we don't talk about is that, solids are crystalline.
Mm.
So we might have taken out enough energy that the water molecules aren't really moving, but we wouldn't consider it to be solid water, ice, unless it's in its crystalline state.
Right.
They have to have that repeating unit to them.
Right.
And they can't just get to that state because water molecules are actually sometimes closer together. We've talked about why ice floats on water, right?
Mm-hmm.
So water molecules can be closer together than ice molecules.
Right.
So if they're really close together and they're cold and they're not lined up in their crystalline state, they'll just stay as really cold water.
Right. Okay.
So then they're not really ice yet. So there's not a point at which we can say if water gets to this temperature, it will definitely freeze.
Yeah.
Which is why I don't believe in freezing points.
Right. And it makes sense because if you were to try to like categorize the state of matter based on its temperature, it'd be kind of dumb because it would have to vary from thing to thing. You know what I mean?
Yes.
It's not like there's a super firm rule that all things at a certain temperature must be either solid or liquid or gas.
Mm-hmm.
So it makes sense that really it's about the structure
Yes.
and the way the molecules are interacting that should be our indicator, not how hot or cold it is.
Right. And we already talked about that with the boiling water, how water boils at different temperatures in different places. It's about when the water vapor is the same as the atmospheric pressure, I think, or I can never remember that definition off the top of my head, but it's basically when the water vapor can turn into gas.
Yeah.
It's not the literal temperature of the water. It depends on so many other things too.
Right.
You know? And so I feel like that's a thing that's kind of maybe overlooked when we talk about freezing points, but generally if water gets to around 0 degrees Celsius or 32 degrees freezing, it has lost enough of its energy that it can't overcome those attractive forces anymore, and it's in this solid state.
Mm-hmm.
But for it to get there, it needs to have its crystalline structure. And usually that needs something that we've talked about before, Jam. Do you remember what it is?
A nucleation site?
Yes, a nucleation site. We've talked about nucleation sites a lot. And it's basically just a made-up point for, this is the best way I know how to think of it, for molecules. So like when we talked about a nucleation site for snowflakes, like a dust or something that the water molecules could start to hook onto.
Yeah.
In the atmosphere, or we talked about it in the Mentos and Diet Coke episode, one of my all-time favorites.
Totally, yes.
It's where all the gas bubbles are able to meet and then overcome the intermolecular forces of the liquid. And Mentos just has a bunch of nucleation sites, and that's why it does its thing.
Right.
So in water, often there needs to be a nucleation site that lets it get into this crystalline form.
Mm-hmm.
Like, there needs to be one trick that you can do is to dip ice into supercooled water, because then the water thinks, oh, this is the right structure. And the water molecules right next to that ice cube line up to it because it's the lowest energy state. So they're like, here's a lower energy state we can be in. Yeah. And then they're like, this is the best place to be. This is the easiest. I'm going to do that. And then it sort of spreads out to all the other ones. They all realize sort of a chain reaction, like, wait, this is the right crystalline state. This is the lowest energy crystalline state. Let's get there because we're not able to move, you know?
Yes.
And so another nucleation site or something that can work to cause a nucleation site is shock. So if you take that water bottle out of the fridge and it's cold and you really gently move it out and then you slam it, when you have that shock impact, it puts just enough energy in that some of them will maybe start to line up and align in the lower energy structure. And then they all realize that that's the lower energy structure. And it almost is like it's telling them, like, this is the way we can be in our best. This is our best life. Yeah. You know, like a trendsetter, like, wait, this is a low energy configuration for us to line up in. Let's all do it.
Yeah.
But it's kind of weird that it doesn't just get in that state anyway.
Right.
And so that's why I think freezing points are a lie. And I think of melting points, even boiling points are kind of a lie, but I think of melting points more and boiling points more. But I also think of these things as tied to the state of matter and not tied to a temperature.
Right.
So that's why I think that really all points are a lie, but I feel like freezing points are the one that's most obviously a lie.
Yeah.
With the super cooled water situation.
Yeah, that makes sense. That's so interesting.
Mm-hmm.
And also, like, what's so funny about the term nucleation site is there's been multiple times recently where I have wanted to use it as if it's a common vocab.
Welcome to my life, dude.
Because, I mean, it's so perfect. It's like, it's like, I want to create a point where this things start. Mm-hmm. And like, there's a lot of reasons you may want to use that in like a meeting, workplace, something like that, whatever you're trying to do.
You're like, we're going to change the way chemistry education is. We need a nucleation site.
Yep. Yeah. We need something to kind of start this reaction, start this thing going on, start this change in the structure or whatever. But like, I'll say that and then I'll be like, I can't use that term. Like I'll stop myself right before and be like, okay, I need to think of something that's non-chemistry to use.
It's so satisfying, right?
Yeah.
It's like nucleation site, like a meetup point or a point where we will gather to create the momentum that we need to overcome these opposing forces or whatever it is. Yeah. I feel like for organizational structure in marketing, that could be a really helpful term.
But like also having the visual, like I don't know if you guys have ever seen the videos of people doing this with a bottle of water or whatever, or if you've done it yourself. But it's so cool because you see it just like spread, throughout the bottle, and it's like having that visual in mind is part of what makes it so tempting to want to say Nucleation Site, because it's like I want this thing that I'm seeing in my head where water's like from one point going and turning into ice slowly. Not slowly fast, but you can see it gradual happen. Is like I want that to happen in real life in this thing we're talking about, or whatever. But
one that I really like is a martini glass. I've seen a martini glass of Supercooled water, and they just put an ice cube in it. Oh, it was so satisfying.
I've never seen that. I'll have to look it up.
I think it just like, it was really easy to see the water and to see the change.
Yeah.
And like, it's just so jarring, like a regular old ice cube into the martini glass.
Yeah.
Yeah, that was a really satisfying one. Maybe a better name for this episode would be how Supercooled water works, but I kind of like the contentious why freezing points aren't real.
Yeah, totally. I mean, giving people some controversy. That's,
Listeners, is that what you want? Some controversy?
If you're listening to this, we've already decided on what the title is, and you're already seeing what we decided on.
Yeah,
So
you'll see.
It's a little too late, but anyway, who knows?
So anyway, that's why I don't often talk about freezing points. And people ask me all the time, have often asked me about freezing point depression. And I'm like, I don't even like that phrase, freezing point depression, because there's no such thing as a freezing point. So how are we depressing it? But that is like a term that's actually used. So I understand why that gets asked a lot. So we've talked about colligative properties before. And colligative properties is this thing that if you add something else into usually a liquid, it'll increase its boiling point. So it'll boil at a later temperature than it normally would, and it will decrease its freezing point. And this is, again, considering all things being held equal. We're not changing the pressure or anything. Like, we're just in the same environment. Adding salt to water makes it take, quote unquote, longer to boil, but just because it's boiling at a higher temperature.
Right.
And the way I like to think of, the other side, I guess I should say before I jump in, the other side of colligative properties is if you add salt to water, it will freeze at a lower temperature.
Right.
So that you kind of have it going both ways, like boiling point elevation and freezing point depression is what they're called.
Yeah.
And the way I like to think about colligative properties, and if you want a more in-depth lesson, you can go back and listen to that old episode about the pot of water boiling. But I think of it as the salt or sugar or whatever you're dissolving in the liquid, in this case, we'll just say water, is like infiltrating. And these infiltrators are making it harder for, on one side, for the intermolecular forces to come together. And on the other side, there's sort of a barrier to getting the water to be able to come out of the liquid. So they're little infiltrators that are getting in and messing things up.
Yeah.
Kind of messing up intermolecular forces, messing up the ability to go to the surface. It's just like, instead of a pure water situation, now you have water and infiltrators.
Right.
And the interesting thing about colligative properties, like freezing point depression and boiling point elevation, is it's not related to what you dissolve in there. It's related to how much you dissolve.
Okay.
So if I put a teaspoon of salt or sugar versus 2 cups of salt or sugar, it doesn't matter if it's salt or sugar. They will increase the boiling point and decrease the freezing point by the same amount.
Got it.
And so that's why we put salt in water that we put down on roads before they ice, is because it essentially, the salt gets in and sort of disrupts the ability for the water molecules to find each other and have those intermolecular forces attracting them. It just breaks up the intermolecular forces, is the best way I can put it.
Okay.
These little infiltrators. And so we salt the water, and then when it snows or there's some precipitation, we hope that it will bring down the boiling point, bring down the freezing point. But a question that I have not been able to answer is, if it's already frozen and then you put the salt down on top of it, because it's not in its liquid state, I don't think that the salt would be able to get into and penetrate and break up those intermolecular forces as well. So it's actually better. And I think why they usually do this is pre-treat the roads.
Right.
So that the salt, I've seen them put down like rows of salt water basically. And then I think a lot of times in Texas, it will rain, sort of kicking up that salt. And then it's salty water on the road instead of pure water.
Yeah.
Quote unquote pure water. Most water that we interact with is not really pure. But
Here's a question off the cuff. Maybe you don't know the answer. Maybe you do. But a lot of towns in Texas, because we don't have just like a ton of winter storms. You know, it's like we have like one a year kind of thing.
Yeah, one a year, but longer and worse. So
yeah. So not all of the towns, maybe including ours, I'm not totally sure on that, but don't do salt, but they do sand afterward. My guess would be that that's not anything colligative about that going on. It's just to add some texture.
That is what I think too, because I think especially after it's frozen, I mean, maybe the sand, like the very small particle sand, is typically silicon dioxide. So like maybe once it's melted, if there's sand in there, it'll do something else, like something similar. But I think that they're not doing that for the freezing point depression because the freezing has already taken place.
Yeah.
I think they're doing it to put some texture on the road.
Okay.
But somebody asked me about like, oh, why does throwing salt on ice make it melt? And I feel like, I mean, we don't have a lot of ice, so I don't have as much experience as like Michigan kids or whatever probably do.
Right.
But my thought is like you could throw throw salt on ice after it's already frozen, and it would just be less effective. Like it would probably melt that top layer, and maybe then once it melted the top layer, it'd get mixed in, you know, and then then salty water touching the frozen water below it, you know, and like slowly work its way down. But it would just be more effective, and I think that's why people pre-treat roads before storms, is if it's in the like thoroughly mixing in the water.
Right. Okay.
So
that makes sense. And ideally, if you do it ahead of time, you might not need to do it later. But if you did do it later, like if you had a lot of ice in it forming and you don't top them, it might be like working from both sides.
Yeah,
you know?
maybe so. Yeah,
something like that.
And I do think again because colligative properties, it's about how much is dissolved, not what's dissolved. So the sand could be doing some of that, but I think the sand doesn't distribute evenly in water the way other things dissolved in water, like sugar and salt.
Right.
You know, so I think the sand is a lot more about texture.
Okay.
That's my theory. I don't know. I'm not let's get our civil engineers or civic engineers, is that what they're called? Our civic engineers coming in here and explain how your city's water freezing process works, what you do in preparation for an ice storm. I'd love to see that in action because for us being in Texas, this is always a theoretical.
Yep.
It's like I don't get to see the saltwater trucks.
Yeah.
You know? So I would love that.
Yeah.
Okay. So that's why we salt our roads. Now, why do you think, and listeners at home, you can also think about this, why do you think we drip our pipes to prevent freezing in the winter? So just take a minute and think about it and see what you come up with.
So this is, of course, helped by our discussion so far. But I feel like you're dripping your faucet. The water's going to be constantly moving. So that flow that the molecules have with each other is continually being encouraged. And it may make it harder, even if it does get super cooled. It might make it harder for them to actually end up arranging themselves into that crystalline structure. Even if it is still possible for it to get cold enough to have frozen. Maybe we're just preventing it by keeping the movement going. Just like I'm guessing bodies of water that are moving also don't freeze as easily, as quickly.
Yes, so that's something I want to touch on. As you said, bodies of water that are moving don't freeze as easily, but they still do freeze.
Yes.
So somebody said that, well, just moving water doesn't freeze, right? But it definitely does. You've seen frozen rivers before.
Yeah.
Haven't you ever watched Frozen? No, I'm just kidding.
I haven't actually watched it.
But that is a good depiction of like, okay, if you've seen a frozen stream, moving water can freeze. But the very fact that it's in motion is a level of putting energy in, like molecules moving around. There's energy in that, right?
Right.
So that's part of it. The other thing I think is I saw someone, I think you're onto something with the not forming the crystalline state, because I saw someone turn on their water and it was freezing as it hit the sink. And then there's like a bigger and bigger pile of ice as the water was pouring out of the faucet really slowly.
Cool.
And they're like, it's so cold out here that it's freezing in the ambient air. And I was like, no, I think that water is super cooled.
Yep.
And it's freezing when it hits your faucet, which had a nucleation site, or your sink, sorry, that had a nucleation site in it.
Right.
So I think it's coming out of the faucet already below 32 degrees.
Yeah.
But I was like, how can I explain that in this TikTok video? So I just moved on.
Totally. It's also funny because I'm like, do you really think it's 32 degrees inside of your house?
I didn't even think of that.
It's like, no, of course not.
Maybe they'd lost power or something.
Oh, yeah, maybe so.
But yeah, that was like, I think that is genuinely what they thought. And I was like, no, that's a nucleation site. Anyway, so I think that's part of it, is keeping it moving might discourage the formation of the crystal structure.
Yeah.
And if you have a hot water moving through your pipes, that is putting energy into the water. Heating it up literally is going to try to keep it from freezing and keep more energy moving through the pipes to keep it from freezing. The bad thing is, if it does freeze, the water expands, which we already talked about that. And so the other benefit is, if your faucet is open, the water has somewhere to go as it expands. So you may still freeze your pipes, but they may not burst.
Right.
So it's kind of twofold.
Got it.
And I have read that some people disagree that it helps, but I cannot see on a molecular level how it would hurt.
Yeah, I mean, I can tell you specifically anecdotally that it helps, because I have our kitchen sink has an exterior, it's on an exterior wall, and it's frozen. We've lived in this house for enough times where it's frozen multiple times, like the
outside, not the pipe,
the weather. But our cold water has frozen and stopped flowing twice. We lived here, but has not burst. It's because I accidentally have dripped it where it's only on hot. So then and that pipe right in that location specifically, on the wall wherever that pipe is coming, around, it's freezing right there. The cold is, but the hot, which is coming from the hot water heater, is not. But somehow it's able to expand in a way where, because water in my house is still flowing, that it's not actually bursting, and I have no idea how. But when I turn it to where I put the sink, if I it's one of those faucets where it's like, it's a gradual thing instead of having two faucets, instead of two knobs, it's one. Put it in the middle, then both are moving, and it keeps it from freezing. But
see, so it isn't. You don't even need to keep. I was imagining the hot and cold coming through the same line.
Right.
But even if you just let the cold slightly move instead of just the hot slightly move, the cold slightly moving helps.
Yeah.
So see, in your anecdotal experience, the moving water was enough.
Yep. And it and I experienced what it was like when it didn't work, and it did freeze, and then we didn't have cold water in our sink. We had hot water though.
I also read, this was on like a plumbing website, and so I didn't reference it because I was like, I don't know if this is accurate, but that cold water a lot of times, like within your house, has outlets, like your toilet is on cold water.
Oh yeah.
And so it has a place that it can expand into.
Yeah.
But that your hot water doesn't always, so it's beneficial to drip your hot water too, because your hot water might not just it's not automatically running the way your cold water can run through your toilet. Right.
And I guess,
but I don't know if that's true. This is pure speculation.
I'm sure it matters immensely, like where your water main is.
Yeah.
And how it splits up. Because I have a sense of it for our house, and probably from the experience of our sink, freezing, stuff like that. I know where some of those problem places might be. It seems like one of our bathrooms, like I don't have to drip it in there because it's interior fully. Yeah. And it's actually not gonna, as long as other things are dripping, that one's not gonna be a problem. Yeah. But I don't really know, like, as soon as our water main comes in, how soon does one part of it branch off over to the hot water heater?
That was something else they talked about, was knowing the furthest sink and dripping that one, because then all the pipes will have water moving through them. Yep. But then I thought, what about the offshoots? They wouldn't.
Yeah.
And then I
could
realized
freeze.
how little I know about pipes.
Yeah. And like how most of us don't even need to know where they are.
Yeah.
Like which order of things gets what first. Who knows?
No idea.
You could maybe pick the one that's first to the corner of your house, but is it actually the one that's getting it sort of last or no? Who knows?
I don't know. I also wonder because our dishwasher drains out into our sink and you can like see it, like where we have the disposal, you can see the water coming from the dishwasher. And I was like, how does the dishwasher water get up that high? Is it just all the pressure of it pushes it up?
Right.
Because the drain is on the bottom of the dishwasher.
Yeah.
Those are the moments I realize that I have a very specific expertise.
And it is so good that other people have other very specific.
I'm so glad there are plumbers in the world that know about how that works, because I'm like, I don't know about this. It's something that I would love to learn, but that I've never thought extensively about, not being a homeowner especially.
Yeah.
So. Well, now we're just off topic. So now we're just chit-chatting, but that is a good look into the mind of a chemist when I think about why we drip water from our pipes, why we drip water from our pipes, why we salt roads, and why I feel weird about quote unquote freezing point and depressing the freezing point. That sometimes doesn't always work.
Yeah.
But really all these things are relative.
Yeah.
Science is so much more gray than they tell you at the beginning.
Yeah. Who can know it?
Somebody once on an offhand comment was like, oh, their thinking is so scientific. It's so black and white. And I was like, science is so gray. So that's it. That's my rant on freezing point that I've avoided for 2.5 years. I hope you all enjoyed it.
I enjoyed it.
Good. I'm so glad.
Yeah.
There's not really a good teach back in this episode because I made you guess on the front end.
Right. And we had danced around this topic a bit in the past, so it wasn't like starting from zero.
Not a lot of new science that you got introduced to today.
Yeah.
But do you want to share something that you enjoyed this week?
Yes, there's something I've been enjoying lately, and it's kind of on topic, actually, loosely. But I have been rewatching the animated hit series Avatar: The Last Airbender.
Ooh, I didn't watch that till I was a grown up.
Same. Actually, I didn't watch it
Really?
until about like 3 or 4 years ago. It was the first time I was introduced to it.
It's so good. It's so emotional.
Yep. And it's also very rewatchable. And I just kind of realized that. And I was wanting a show that I could, like, after the kids are in bed, I could watch and like also like do dishes, or like watch and also clean up or pick up toys or whatever. And it's like, because I've seen it once before, it's okay that I'm like part paying attention because I remember some of it. But the story is interesting enough, and there's enough I forgot that I'm like excited about it and enjoying it again.
That's so fun.
That's been fun, and it's a little on topic because, of course, if you've watched the show, you recognize the melting and freezing and kind of stuff of water for waterbenders in the show is a thing. So it's loosely
all
connected.
they're doing is moving around water molecules.
Yeah, they're all just chemists. If you think about it.
Kinda, yeah. Chemists, alchemists.
Yeah.
We're all on the.
All those people are just benders.
I will say though, that Mason, I think, is also. Did you tell him he's rewatching? I walked out the other day of a meeting and I was like, "What are you doing?"
I did tell him,
and he goes, "I'm watching Avatar." I was like, "Where did that come from?"
Yep.
You got him.
I got him, dude. I think I told him about that a couple weeks ago, actually, when I first started.
Yeah.
But. Yeah, I forgot I had told him.
Yeah.
For a second, I was like, no way, he's watching it too? It's like, oh, wait, I did that.
It's sort of like he'll just go through phases. Like for a while, I was out of town a lot, and he was watching, is it Bear Grylls, the guy in the wild?
Yeah,
and
there's a couple, but he's the main one, I think.
Since when did you watch that? He's like, I don't know, just in the mood.
Yeah.
So he'll just go through weird phases where he rewatches like parts of a show. So I bet you said Avatar, and he goes, that sounds good. I want to watch that.
Yeah. Well, it's also nice whenever there's an overwhelming amount of content and it's something
right.
Like, it's not the best to like have that be your policy forever. But it's like, oh, I know I like this.
Yeah.
Why not?
Yeah.
No risk.
No risk. And if you get anxious at all, which no spoilers, but there's an episode where somebody gets got, and I was like really stressed, and I paused it and made Mason tell me if they survived or not. I was like, I can't live like this. I need to know. On a similar note to yours, actually, my exciting thing is that I went to a hockey game.
Nice.
With my brother.
Nice.
And hockey, as some of you may know, has ice on it. Ice involved in it. And
it has ice on it.
The hockey rinks have ice on them. And we sat right next to the ice. I have never done that
Nice.
before.
The sort of action zone. I was about to say splash zone, but I guess it'd be like the frost zone.
The frost zone. Yeah, my water bottle stayed so cold.
Nice.
Yeah, I've never sat that close to the rink before. So they say like on the glass is like the hockey phrase for it. You know, like, oh, you're on the glass. You're right there where everything happens. And it was like being in the game. Like I kept forgetting to participate in the like big crowd things that you do because I felt like I was in it.
Yeah.
It was really fun. It was really fun to go with my brother. Kind of a once in a lifetime type thing that I've never done before. A new experience. It was really, really cool.
That's cool. That sounds awesome.
Yeah.
Yeah.
So, fun brother experience. I really enjoyed it.
Did any fights break out that you were like right up close to?
No, I don't really super care about the fights, but my favorite player switched teams and he was visiting. And so I held up his old jersey and he saw it and came and like tapped on the glass and like bumped it with his arm and sat there for a while playing with the puck. And then I forgot to take a picture because I was so excited.
Right. Yeah. You were in it.
You
were there.
He's right here. It was so exciting. And then I forgot to take a picture, so I have no proof that happened.
Yeah. Well, you know, the good thing is I think they film those games. So.
Not that part. That was warm-ups.
Oh, okay. I was like, somebody probably has video of it.
So that was exciting and really fun. And yeah, that's my happy thing. All the ice, all the water and ice involved.
Yeah. That's super cool.
Awesome.
Literally. You know what I'm saying?
Well, thank you so much, Jim, for listening to my rant. And thanks to my brother, Anthony, for taking me to the hockey game. That was so freaking fun. And to all of our listeners for coming and asking about what happens at the molecular level of water in the winter months. I love those questions. And for letting us get to do what we love, which is help people love chemistry.
Yes, and thank you for teaching us. Thank you for teaching us the inner workings, the molecular level of this very interesting, but also very everyday, very seasonal, you know, kind of deal that we have to deal with, and helping us understand it. Melissa and I have a lot of ideas for topics of chemistry in everyday life, but we want to hear from you. We want to hear your questions, just like this episode. It's a bunch of questions that you guys have sent us in. So if you have questions or ideas, you can reach out to us on our website at chemforyourlife.com. That's chemforyourlife.com to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the cost of making it, go to patreon.com/chemforyourlife or tap the link in our show notes to join our super cool community of patrons. If you're not able to do that, you can still help us by subscribing on your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. Jam Robinson is our producer, and this episode was made possible by our financial supporters over on Patreon. It means so much to us that you want to help us make chemistry accessible to even more people. Those supporters are Avishai B., Bree M., Brian K., Chris and Claire S., Chelsea B., Derek L., Emerson W., Hunter R., Jacob T., Christina G., Lynn S., Melissa P., Nicole C., Stephen B., Shadow, Suzanne S., Sam N., Timothy P., and Venus R. Thank you again for everything you do to make Chemistry for Your Life happen.
We'd also like to give a special thanks to our team of reviewers who reviewed this episode. And if you'd like to learn more about today's chemistry lesson, check out the references for this episode in our show notes or on our website.